Hi there, and welcome back to this channel. In this video, we're going to be discussing the concept of hybridization. Now you see, hybridization is a very important concept in organic chemistry. It helps us to understand the way carbon behaves in several organic molecules. This is just like the way in biology where different species or strains of organisms are interbred to give rise to a new species known as a hybrid. Orbitals could be combined together linearly or mixed linearly in order to generate a new type of orbital, which is known as a hybrid orbital as well. Now, this hybrid orbital is usually different in form and structure than different from the starting two or more orbitals that started the hybrid. So you can mix two or more orbitals to form a hybrid orbital. All right. So now historically, in 1858, you see Auguste Kekule, the guy who proposed the structure of benzene in 1865. He came up with the idea of tetravalency of carbon. And this was also the idea that this guy, Archibald Cooper, in the same year, but independently, came up with this same idea of tetravalency of carbon. Now, carbon was tetravalent, means that it was capable of forming 4 bonds. And this was one of the major confusion to the understanding the way carbon behaves in organic compounds. Now, the reason it was a confusion was because this idea of tetravalency at this time could not be represented because chemistry was still being viewed in two dimensions. Now, it wasn't until 1874 when Jacobus van 't Hoff and Joseph Lebel. Now, it wasn't until this year that both of them worked together to help to understand the 3D model of organic compounds, of chemicals. So we were able to begin to view chemistry in 3 dimensions through the help of Jacobus and Joseph. So it was until this period, it was impossible to represent the tetravalent nature of carbon, although it was a correct proposition. Now, the confusion was this, that the electron configuration of carbon is 1s2, 2s2, and 2p2. Now, using Hund's rule, and Pauli's exclusion principle, we can generate the orbital diagram. The orbital diagram will be something like this: 1s2 here, so this is 1s2, and the 2s, that will be this way still. Notice the way I'm filling it using Hund's rule. It says that we should fill them singly first before pairing. Now, the rule does not apply here yet because these s orbitals are non-degenerate. Then p orbital is the first degenerate orbital. So we are going to have to follow it here. We have 2s2 here, and here we have 2p2. So here it is degenerate into 3 orbitals. So since it is degenerate into 3 orbitals, we have, let's make it into a box this way. So since it degenerates into these 3, we have the px, the py, and the pz. So we have 1 and 2. Is that okay? Using Hund's rule, we are supposed to fill them singly first before we pair. So it will be wrong to say 1 and 2. This will be wrong. So notice that I am following Pauli's exclusion principle by filling with opposite spins. That was what his rule says, that they might have the same number for all 4 quantum numbers, but at least but will differ essentially in their spin quantum number. All right. So now the confusion was that seeing that carbon had only 2 unpaired electrons here, it should coordinate to only 2 bonds, with only 2 bonds. But actually, this guy and Cooper discovered that carbon actually coordinated with 4 bonds. Now, how was this possible? Then, in 1931, Linus Pauling was able to come up with the idea of hybridization in order to explain this phenomenon. You remember Linus Pauling, the guy who designed the electronegativity table of atoms on the periodic table. So it is determined that scale, we call it this Pauling scale, that has the electronegativity value of all the elements on the periodic table. So this guy came up with the idea of hybridization in order to explain how carbon was able to, even though having, even with having only 2 unpaired electrons, is able to coordinate to 4 bonds. Now, this was his explanation. Now, so ideally, these two seem to be in almost equal energy level. In fact, they are actually in the same energy level. As you go up, you attain a high, you increase in energy level. This one is the first energy level at a lower energy. This is a second energy level. Now, this is slightly shifted a little because S and P are not of the same energy. So, although they are in the same energy level. So, this is known as the ground state electronic configuration of carbon. So this electronic configuration is the ground state electronic configuration of carbon, which will be written as what? 1s2, 2s2, and 2p(x1) and 2p(y1). So this is the ground state electronic configuration of carbon. So he proposed that that whenever carbon wanted to bond, it attained what is called an excited state. And in this excited state, that carbon is able to promote an electron from this place into this place. Why? Because number one is that they are in the same energy level, so they are almost of equivalent energy. So because of that, in the excited state, carbon is able to promote 1 electron into this place, so that we have something like this. So I'm going to be drawing only these two, isolating these two. So I have 2s and 2p. So carbon that initially had 2 here is going to promote 1 electron here, so that each of these now have single electrons. Hence, we now have what? We have 4 unpaired electrons. And to this unpaired electron are what other atoms now form covalent bond with. So that is the reason why carbon is able to what? Form a tetravalent bond, form 4 covalent bonds. So this was his idea of hybridization. Now this concept of excitation does not still explain the way it forms different bonding, different types of bonding, because there are different types of hybrid that carbon even coordinates to. All right, and this is where we come up with the 3 types of hybridization that exist. But this excitation helps us to know that carbon is able to form 4 bonds because it promotes 1 electron into the 2pz orbital. All right, so that we now have 2s1, 2px1, 2py1, and 2pz1. All right, remember that what's the shape of the s orbital? The s orbital is called the sharp orbital, and we said it has a spherical shape. It has a spherical shape. And then the p orbital is called the principal orbital, and it's the first degenerate orbital, right? It's the first degenerate orbital, and it has a dumbbell shape. And it is degenerate into what? 2px, px, py, and pz on the x, y, and z planes. On the x, y, and z planes. The y-axis, the x-axis, and the z-axis is basically an axis that conforms with. Now, it is just basically the axis that enters into the body and comes out of it. As you look at it from the camera, it is the axis that is entering into the body and coming out of it. We have this axis, and another axis that is entering the body and coming out of it. That's the z-axis. All right, so that we have a dumbbell of here of this shape here, and a dumbbell of this shape here, and a dumbbell of this shape here. All right. So now, what are the three types of hybrids that we could have? Hybrid orbitals that can exist. The first one is the SP3 hybrid or SP3 hybridization. Now, the SP3 hybridization means that there is only one s orbital and three p orbitals have been hybridized. So we have that one s orbital is hybridizing to what? Three p orbitals. So notice, these two want to hybridize. So if these two want to hybridize, the hybrid that will be produced will be in this way. It will look something like this, somewhat like this. So it will not look exactly like the spherical shape, and it will not look exactly like the dumbbell shape. It will look something like this. So this plus this is going to give us a hybrid that looks somewhat like this. Or you could also draw it this way. So now, in this SP3 orbital or hybridization, we have that one s orbital is hybridizing to what? 3p orbitals. So that we have something like this. So this is the s orbital. Now 2px, 2py, 2pz. So this is now the orbital that is formed, the new orbital that is formed with the shape something looking somewhat like this. So notice that the shapes are what? Different from the forms of the initial orbital. Now, what does this tell us? This tells us that of the four characters that are acting here, the S character takes 25%, while this character takes what? 75%. Now, if everything, the entire four represents 100%. So this is only one, so it took 25% of the entire hybrid. Now, what are the characteristics that this hybridization conforms on the molecule? The first characteristic is the tetrahedral shape. Tetrahedral shape. Remember that Joseph Lebel actually proposed that the four bonds that this guy carbon coordinates to was oriented at the four corners of a regular tetrahedron. So that the four bonds that this guy coordinated with are oriented on the four ends of a regular tetrahedron. So this SP3 hybridized is what makes it so that it is able to coordinate to four bonds that are oriented at the four ends of a tetrahedron. Now, the other characteristic that it bestows upon them is that the bond angle between the bond angle between them is 109.5 Granot. Now you see 109.5 degrees. Now you see that tetrahedron differ the bond angle between each of those molecules is 109.5 degrees. Now, it also bestows upon them saturation. So the compound form is going to be what? Saturated. The compound form is going to be what? Saturated. And what does saturation mean? Saturation means that there is no, once atoms are bonded to all of this four, there is no other point in which compounds can be bonded. And that is why, because they are saturated, they can only engage in what? In substitution reaction. Substitution because electrons can no longer be added. Electrons can only be substituted. Electron can only be substituted, can no longer be added because they are what? Full. They are filled up with electrons. So that is the meaning of saturation here. All right. We also said that the bond that will be formed, all of this will form what is known as a sigma bond. A sigma bond, which is the strongest covalent bond, the sigma bond. All right. So we have this, the shape, the bond angle, the bond that will be formed. So, and we also said that the what? It will be saturated. Now, the bond strength is also 348 kilojoules per mole. And of course, it has a bond length of 154 picometers, which is longer than the remaining type of hybrid, and it's the longest. Of course, picometer is not long at all, but relative to other type of hybridization, 154 picometers is longer. All right, so these are the characteristics that SP3 hybridization bestow on the molecule. Right. Now, the second type of hybridization is the SP2 hybridization. Now, seeing from what we had there, we said that the SP3 was 1s and 2p orbital. So the SP2 would mean what? 1s orbital hybridizing is what? 2p orbitals. So notice, what we are going to have is going to be this, like this. So we're going to have the 2s, the 2px, and the 2py. Then this guy, 2pz, is isolated. Is not forming an hybrid. We have this as our hybrid. So what does that mean? This means that this is still going to have this shape. This guy will have his shape, his hybrid shape. But this guy will retain his what? Its original dumbbell shape. This will not be changed in shape. Is that okay? So what does that mean also? That in this molecule, in this hybridization, each of them will be contributing about 33.1/3% of in character in the hybridization. Unlike here where S was just 25% of the entire hybrid. Here, S will occupy, each of them will occupy 33.5% of the hybrid. Is that okay? Now, what characteristics of does this hybridization bestow on the molecule? The first one, the shape is going to be trigonal planar. Trigonal, the word tri means three and gon means side, so means triangle, isn't it? So triangular planar, that's the meaning. All right? And the bond angle is going to be what? 120 degrees. Then it is going to be an unsaturated hydrocarbon. Now, unsaturated because of this. Let me explain what that unsaturation means. Unsaturated, it will be unsaturated because only these three are engaged in the hybridization. So if only these three are engaged in the hybridization, it means there is still one more orbital that is going to be what? Valent, that is going to contain a valent electron. So what this remaining orbital is going to do is that it's going to overlap with another 2pz orbital of another carbon laterally, so that the what's it called? The valent electron here, the unpaired electron here, is going to form bond with another 2pz orbital of another carbon. Is that okay? But it's going to be just a lateral overlap of those two orbitals. It's going to be a lateral overlap of those two orbitals, not the hybrid, not an hybrid orbital. Now, the reason why this hybrid is formed, these hybrids, the reason why they are formed in this way is so that there will be enough space for the bonding atoms to attach significantly to the carbon molecule. Is that okay? So that is the reason for hybridization itself. That is the reason. Now, I now said that this guy is going to give rise to a separate type of bond, and it is unsaturated. I will explain that further. But let's go to the type of bond that will form. This guy is still going to give us a sigma bond. Now, we have only one sigma bond here. But in this case, we're going to have one other bond, which is known as the what? The pi bond. So we have one sigma and one pi. This bond is known as a pi bond because it's formed by what? Lateral overlap of unhybridized p orbital. So that is what gives rise to what? To the p orbital, to the pi bond. So the electrons that will be there will be called pi electrons. Is that okay? Pi electrons because they are what? Unpaired. Now, and it is unsaturated because since it's unpaired, it still confers on that molecule the tendency to what? To want to coordinate to another molecule. Is that okay? So it still feels sort of electron deficient, unsaturated. If you say someone is unsatiated, it means the person is still hungry, isn't it? So the same way. So it probably means the person has eaten but is still hungry. So the same way unsaturated here means that there is still space. All right. So that space is because this guy is what is unpaired yet, even though there is a lateral overlap. So electrons are there, but they are what? Unpaired. Is that okay? So then the bond length here is 134 picometer. So you see that it's actually longer. This guy is actually longer than the SP2 hybridized orbital. Now the SP3 hybridized, the last orbital is the SP hybridized orbital. And what does that mean? We have only one S hybridizing to what? Only one of the p orbital. So with that, what do we mean? We mean that we are going to have the 2s and the 2px. Only the 2px we hybridize in this case. So we have this and this, and we now have these two unhybridized. The py and the 2pz, they are unhybridized. So they will retain their what? Their dumbbell shapes. Why this guy what? Form the hybrid orbital. Is that okay? Now, what does that mean? It means that there's going to be two lateral overlaps now. So we are going to essentially have what? 2 pi bonds and what? 1 sigma bond. 2 pi bonds and 1 sigma bond. So let's talk about the characteristics we see. Now, so starting with the shape that is going to have is a linear shape. It's a linear shape. Why? Because there are going to be 3 types of bonds here. There's going to be the first sigma bond, then there's going to be 2 pi bonds. Those are three bonds, so which gives it a linear, makes it a linear molecule. So you are going to essentially see something like this. So this is on a straight line. Is that okay? Now what do we have here? The second characteristic is the bond angle. Now angle on a straight line is what? 180. So we have 180 degrees. Is that okay? So we also have that the molecule will be unsaturated. And in fact, this one will be more unsaturated than this guy. Why? Because there are 2 unpaired electrons here. There are 2 unpaired electrons. So it is unsaturated. Hence, it will be more reactive than this guy. Now, we have that we are going to have 1 sigma and what? 2 pi bond, as we said there. Then, and we said it's bilateral overlap of what? 2 unhybridized p orbital. And the bond length is also going to be what? It's going to be what? 120 picometers. All right. So, and it is on this basis that hydrocarbons are divided into alkanes, and alkynes. So alkanes essentially have what? 2 SP3 hybridized. Alkanes are SP3 hybridized, alkenes are SP2 hybridized, and alkynes are what? SP hybridized. And for that reason, alkanes only undergo what? A substitution reaction. A substitution reaction, why? Okay, we've written it. A substitution reaction, why? Because electrons can no longer be added or removed. Electrons can only be what? Substituted, exchanged. Is that okay? Because this guy is already filled up. Electrons are already filled up. When this guy reacts with other atoms, electrons fill it up. So it is filled up. That is the saturation there. It is filled up. So what can we do? We can only what? Substitute. Hence, they are called paraffins. The word paraffin is got from 2 Greek words, para and affinis. Affinis means love. Para means weak. Is that okay? So it means that it has weak love for reaction. It is less reactive. It is the least reactive. Is that okay? So this guy will be more reactive than this, and this guy will be more reactive than this. Is that okay? Now, these guys are going to undergo addition reaction. Addition reaction, why? Because they have electron deficient center here. Why? Because they have unpaired electrons. So these guys can coordinate to one more bond. Is that okay? Electrons can still be added, and that is the meaning of what? Addition reaction. This guy also, in fact, undergo more addition reaction, or even higher addition reaction. So here, where you'll be adding, how many molecules will be adding here? You'll be adding 2, how many atoms will be adding here? You'll be adding 2 atoms, and that is why you have this. You are going to have a shape like this, C double bond, this. So that when this guy breaks, one of these bond will, one of the electron here will form a covalent bond with another electron. One of the covalent bond here, one of the electrons here will form another bond with another electron from another atom. Is that okay? So when this one breaks, is that okay? So and this guy is going to break twice, undergo double addition reaction. Right. So this is what we have for hybridization. In the next video, we are going to be talking about some more properties of these hydrocarbons, and see you in that next video. Make sure you subscribe to the channel and share this content with your other friends that might need it. See you in the next video. Thank you, and God bless you.